Okay. So let's start with 38.
Pretty easy.
No, because it's like
Why?
exactly. It's a ratio. So like you multiply both by 2. That's right.
Why are we multiplying both by 2? What are you talking
It's a
about?
ratio.
Yes.
38.
Hey Shaq, are you an AP?
You have to do 2Q1 and 2Q2.
80 points first
Huh?
place.
Let him cook.
What are we
What's
talking
the
about?
what's the answer called to? Is it to the negative 11 power?
Negative what?
11 power. And a decent GPA.
Okay.
38.
So let's talk about 38. There's a whole bunch of things you need to do to get to that final answer. Starting with the idea that you have a diameter that's in millimeters.
Gavin.
So one of the first things that you need to do is find the volume. Then you can find the mass, because you know that density is mass divided by volume. So step 1 is to find the mass. Okay? If you're in kilograms, that's 10 to the negative fifth. Okay? That's just the mass part of it. But this is going to be important. That's in kilograms. Your molar mass is in grams per mole. So you're going to get the mass in kilograms from the density. Then roll that into a mass in grams. Then it turns into a stoichiometric problem. So you're going to have so many grams of copper. And then you know the molar mass of copper, 63.55 grams of copper per 1 mole. You know the moles. You know how many particles there are. Now, the atomic number of copper is 29. So there's 29 electrons per 1 atom. So the total number of electrons is a big. Okay?
That's pretty big.
So the total number of electrons. Now, here's what I want you to think through. This is basically something the size of like a marble. Okay, a very small one. And that's like 10 to the 11th electrons on that small little bead. So you also know on 38 that it's charged to positive 50 nanocoulombs. So because of the 50 nanocoulombs, this is an important differentiation. To get that charge of 50 nanocoulombs, did we add positive charges, or did we take away chihuahuas?
Take away the chihuahuas.
Why didn't you change the number of St.
It's
Bernards?
impossible because the protons are so stuck in the
Because what determines the type of atom?
protons.
Only the number of protons. Okay? So if you try and add on these vast number of protons,
Change everything.
yeah, you change the chemical structure of it. Okay? So
You add a proton.
you add or gain chihuahuas. So if you know that, if you know the total number of charge, and you know it's 50 nanocoulombs, convert that into coulombs. What's the charge on each chihuahua?
1.6 times the negative 19.
1.6 times 10 to the negative.
Oh yeah.
So what you're trying to find at the end of the day on 38, what fraction of its electrons have been removed? So the only way you can do that is take fractions divided by fractions. Okay? So the fraction of electrons that have been removed, if it's not a percentage, just a number, is going to be an GPA times 10 to the minus 11.
Yes.
Okay? So there's a whole bunch of things that you have to go through to get to that point. On 34, while we're on that page, so with this one, it's basically, it's this torque problem that we talked about yesterday. On 34. So they've gone through all this explanation. Here's the short story.
She's just laughing.
I swear to God. Sit.
60 plus 60 is 120.
I just don't
120
understand.
plus 60, the triangle is 180.
So the dipole moment can be modeled as two opposite charges of magnitude. They actually gave that in Coulomb separated by a distance of 100 micrometers. What's the maximum possible torque on a sphere? So this is what we talked about yesterday. So you've got a positive and you have a negative side, and it's being subjected to an electric field. Okay? So they've given you the value of the electric field, 4 times 10 to the 5th newtons per coulomb, so you have that value. So the equation that we came up with yesterday to calculate that torque,
T equals F.
the overall torque is going to be what?
FR.
Well,
Echo. FRL.
echo, right?
What was it asking?
So your answer to 34 should be something times 10 to the negative 13.
No!
Holy Pete, dude. He said 34.
Your signs are wrong.
Wait, is it
Right.
does it start with a word or from?
Where is it wrong? For which one?
Your answer to 34
What question?
64. What was it asking for?
should be 10 to the negative 13.
Two equally charged. What is the charge of the
Now,
No, you have to find
What distance did you use? Did you use 1 meter?
1.4 times.
let's talk about 66, because you have to understand 66 to understand what you need to be able to do in the lab today. Okay? So let's make sure everybody's cool
What'd you get
with
for 66?
66. So this is what I tried to model yesterday. So here's
It's
this
rough.
electric field, and it causes a 2-gram mass in figure 2066 to hang at an angle. What is theta? So you got your electric field going like this. Okay? That's going to be important. So if you look at this, this thing is going to swing out here like this. How do you know that that sphere is even charged?
It's knocked straight down.
Yeah. If what would a neutral sphere experience in an electric field?
Nothing.
Absolutely nothing. Okay? So this is why neutrons were so hard to find. Neutrons were hard to find for 2 reasons. They're bound up in the nucleus and they don't have a charge. Okay? So that's why neutrons are incredibly difficult to analyze. So you got the value pushing out like this. So you're told on this one the charge on here, which is 25 nanocoulombs. So you can find the value of the force. You can use FEC to find the value of the force. But here's the tricky part. That force is your electric field force. That's this side of the triangle. So that's your electric field side. Somewhat analogous to a centrifugal force calculation. Okay? So that's pushing this out. What else can you find?
Gravity.
Gravitational force. Why?
MG.
There's no the mass, right?
Yes.
So you know the mass and you know the gravitational force, so you can find this side, which is also that side. Okay? So if you remember this in terms of this lab today, whatever the weight of that is whatever is also going to be acting upward. So here's what you've got. So you can find this. You also know the force from the electric field. You're trying to find this angle. Okay? Now, in this situation, that's all you have to worry about is finding. They could have also easily said, hey, what's the tension in the string? They didn't. But how would you find the tension in the string? Yeah, you just do the Pythagorean theorem, because you would know these two sides. So your answer to 66 should be in the mid-teens.
Like sophomore age?
Probably sophomore age.
Okay.
Freshman to sophomore.
He was talking about 80. I was confused.
64?
Yeah, we got different.
I was like, does he mean like
Okay,
or something? Like the numbers that end.
so let's talk about 64. Because, again, 64 is going to be very, 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 very relevant to the lab that you're going to do today. Okay?
What'd you get?
Nope.
What?
Nope.
What is it? Is it just on the three?
With a what?
The three.
No, that's
What is the
not
magnitude?
right.
Magnitude.
In nanocoulombs? 10 to the third.
Wait. In the thousands?
In nanocoulombs.
Oh, no, I got it. Holy.
Okay. So, let's talk about 64. Because this is what you have to be able to do in the lab today. So, you got two 3-gram spheres, right? So, here's the deal. Once you start with this idea, once you know the mass, what can you find? So, you know your FG, which also means you know the upward side of the triangle, right?
D.
Go with that.
Yeah.
Got that. Now, you have a 1 meter long thread repels each other equally as shown what's the charge on Q. So you know this is 1 meter here, right? And you know this angle, they were nice and said, oh, that's a 20-degree angle, right? So here's the deal. You can find that upward side because you know it's 3 grams. Convert that into kilograms, old school. You can find that side. So, what do you know about these charges? Are they going to be positive and negative? Or
They both positive.
they just know they're going to have the same charge. Okay, and you assume this on today's with the lab you're going to do today. You just assume that they're equally charged. So what's creating? There has to be some force pushing these apart, right? They're the same charge.
Yeah.
So you know F equals what? Okay, Q1, Q2 over
Q2 R squared, D squared.
D squared. Okay, R squared, whatever you want to call it, right? Now, so here's the deal. Can you find the value of the electric field force?
Yes.
Because you're trying to find this side. Okay? That's what you're trying to find. But if you know this, okay, and you remember this from lab day, I'm going to give you major hints on how to do the lab today. If you know this side here, you know this side here. And if you know this angle, you can find the value of this. Right? Okay?
Yes, Papa Bird.
Oh.
Okay? But, what are you going to use for the distance? You know this, you know that length is 1 meter.
We gotta use.
So you got to do a little bit of trig action to find
I didn't. Wait, what's numbers is this?
What?
Bro,
Which
I'm literally
one?
lost. I'm literally lost.
The final
I don't know what I'm
answer.
doing. I don't.
Okay. On 64,
I feel like
That's what
Okay.
it is.
on 64, when you get done, if you're in, well, it just depends on if you want to work in coulombs or nanocoulombs. But your answer to 64 is going to start with a 7.
Yes, I got it.
I like it.
I got it right. The only thing I messed up was because I did it double.
0.01.
Because it's the distance between those.
Yeah, because that's 2 times 2.
Uh-huh.
What's your distance then? What did you do wrong then? What did you do wrong? Did you square root it? Because it's useful.
Try moving a little bit back.
Oh, yeah.
Did you square root it?
So, assuming that these two charges are the same, which they are,
Q squared.
what do you get?
Combination.
Q squared.
No way.
Bro. What are you doing?
Nah, he's just pranking us.
Yo,
Okay.
you did your force is completely
Sunglasses on.
It's way too bright.
Yo.
What's going on?
On 40.
0.021.
Now, but anyway, let's talk about this problem.
That's the only thing that's wrong.
So,
Wait, 40?
in reality,
Oh, I was dividing.
you have this repulsive force pushing them apart. Okay? But they both have a mass of 3 grams. So, yes, you do have a repulsive force. But what's trying to draw them together? Gravity. So technically, there's a gravitational force between these two objects. And again, remember this from the lab today. Which is going to be big G M1 M2 over R squared D squared, or whatever you want to use. Okay? So technically, there's a little bit of gravitational force pulling these together. Okay? Enough to worry about? No. But technically, there's a little bit of a gravitational force holding them together. So, that's going to be relevant to question number 40, or problem 40, I should say. So on problem 40, you got 2 protons, or 2.0 femtometers apart, which is a really, 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 really small distance. But it has to be that close with the strong nuclear force to hold them together. So you've got the 2 protons. They're really, 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 really close. Technically not touching. Okay?
They never touch.
Technically there's a distance between them.
Between everything.
Now, but here's the reality, and you all have seen this. What are those 2 protons don't want to be near each other?
No.
Why?
Because they don't like each other.
They don't like each other. They're both positive charges.
They want to push away.
So this became the problem with the results of Rutherford's work. So Rutherford comes along, and remember he shot the alpha particles, which are a helium nucleus without the electrons, okay? And he shot these at these gold foils. And he figured out that they were positively charged because oddly enough, and now this makes more sense, now you have a deeper understanding of what physics is. So he shot them between basically a parallel plate capacitor. So he would shoot these particles through, and you have a positive charged plate, and you had a negatively charged plate. So again, you could not see these particles. They are infinitesimally small. It isn't even an entire helium atom. It's the nucleus of a helium atom.
So that's really small.
Okay? So everybody has this vision of like, oh, it's like marbles, and he's shooting them through. And he can see where the marbles go. No! He had to have a phosphorescent screen that when these particles would hit the phosphorescent screen, you would see a flash of light. So he had a box that had thorium, I want to say like 238. It's a radioactive source that would randomly kick out these particles. And it isn't like it was a gun where he was shooting them out. So he had one small opening And so the particles that would come through, he knew which direction they had to be going. And they were going straight, and he had that phosphorescent screen that they would go straight through, because that's where you would see the flashes of light. So then he put the positive and negative plates to create an electric field. So the cross section of that electric field, so here's the two plates, positive plate, negative plate. Okay, it's like a capacitor we showed you all yesterday. So if he's shooting that alpha particle through there, which direction is it going to go?
Down.
Downward. So this is where you can do some serious math. Oh, okay. If this is positively charged, which it is, it's going to go down for two reasons. Why? Same charge, so it's going to be repelled by the positive plate and attracted to the negative plate. So this is going to go on a path like this. True?
Sweet.
This looks a little bit like a projectile motion problem.
Ooh, X and Y.
We did this.
Yeah, you should have
No,
Lima
no.
So if
The
you
Lemming
do FEC, and if you know the value of the electric field,
Oh, you can solve it. I wish we do that.
oh, that would have
Like
been
20 weeks ago?
complete overload. Okay, that would have been complete overload. Okay,
Wait, you guys did this?
so
Yeah, we did
Now,
like a lemming problem.
if it's an alpha particle,
So smart.
if it's an alpha particle, what's the value of Q?
1.6.
Negative 16, right?
1.60.
Should be 1.6 to the power of negative 19.
No, I said that. Oh, wait, it isn't? Alpha particle, what is that? Alpha particle?
Wait,
Two. The charge is 2.
No.
It's alpha particle?
The elementary charge?
No.
I just said that.
Third time.
Are we talking about math right now?
Is it 1?
No, just what
Zero.
they said. times two.
1.6.
Yes. 1.6 times 10 to the negative 19
Yeah.
times 2.
Oh.
Oh, because it's plus 2.
Oh. Because it's two.
That's a big thing.
No.
It's
It's two because it's
Because
repelled and
an
attracted.
alpha particle has a charge
Two
of
forces.
plus 2.
Oh,
They
that's.
always do.
Oh, that one specifically? Okay, alright, we're back in the game.
That's a
All right.
special alpha particle, man.
Yeah, I didn't know you were talking
We were
about
thinking
that.
about regular.
Every alpha particle has a charge of plus 2.
Wait.
I didn't know that. What even is alpha
No.
particle?
Yeah.
It's the
Bruh,
thing with
it's-
alpha decay.
It's what?
The thing with
I also
alpha decay,
don't
where
Yeah.
it loses a helium that has no
It's
no
stripped
electrons.
electrons.
Yeah.
Yeah,
So
two
it's the
protons, two-
helium nucleus without the electrons.
Okay.
So the charge on it would be 2 times 1.6 times 10 to the negative 19.
No way.
So here's a radical concept. So if you knew the electric field and you know the charge, you can calculate
F.
force.
No more lemming
Ooh,
problems.
force equals
MA.
mass times acceleration.
No freaking way.
Ah, you can find the acceleration.
Hey, no more lemming problems, dude.
Oh, it's living problems on steroids.
Yeah.
Okay. All right.
We need Lemming as a backup.
You couldn't imagine.
All right. So
Just a
on
lost
40,
in
because
Let
if
me
40
check my
starts
answer real
wrong,
quick.
everything is going to be wrong.
Oh, wait, for which
The electric force
For 40?
on 40 on A
Around your
should
age.
what?
Around your age.
Yeah. Unfortunately, my age is bigger than that number.
Divide by 2.
Oh, whatever. Okay.
Again, 60 to 30, bro. You're good.
60.
Wait,
Age should be like double your age, right?
The way Brian looked at him. Chat that.
Wait, it should start with the 6.
Wait.
Okay. So your answer to B, the exponent on 40B, this is where you got to go F equals big G M1 M2. Okay. This is not asking for the mass times 9.8 meters per second squared. This is the magnitude of the gravitational force on one proton due to the other proton. Okay? This is not mg. You're not talking about a gravitational force.
He said turn his age.
So that answer on 40B should be something times 10 to the negative 35th.
Let's go.
Oh, I'm like slightly off.
What?
I have a question for you.
So your overall answer on 40C, which is what you're ultimately trying to do, when you're trying to find the ratio of the electric force to the gravitational force, that should be something times 10 to the 36. Okay?
See.
So, again, you have to understand the magnitude of this problem. When Rutherford published his results, and he said you have this very, very dense positive charge, they did not know how to handle it. They were screwed because they literally had to throw out every atomic model that they had up to that point because it didn't make any sense. So they had to come up with the strong force, which oddly enough had to be stronger than the repulsive force. So what you found on 40A was the value of the repulsive force due to the electric field. So whatever force that you had that held them together had to be bigger than that answer to 40A. Okay. Why?
28. I'm confused, like, is it like two capacitors, one's positive, one's negative? It's talking about the electric field.
Question 28?
Probably 28. What? No, can you put your lanyard on real quick?
Wait, is this my?
Yeah.
No. Huh?
Oh, he's talking about the plate.
Hold on. No,
Problem?
I haven't heard that much.
Hold on, I gotta find it.
Check.
Dude, I swear it's zero.
Anything
Okay.
my job.
It's, I swear it's zero.
It's not.
We're good. It's not. Okay.
What are we doing?
We don't know. We don't know, man.
Dude, you're trying to get kicked out of class.
Never worked.
Sorry, I'm being an honor.
Let me get this drawn out.
Yeah, I'm just always an off now.
No.
Yo, it's either zero or it's like 4 times. I love how you denying
When you be bored, it is 4 times.
It depends on like if it's positive, negative,
No, hey,
or
Wyatt.
if they're positive.
Wyatt.
They cancel out.
You're thinking way too deep.
I don't know if you did that right. I should know what it meant.
I hate how this
No, I mean, that's what I got. I think your work is just like randomly everywhere, but that's it.
Shanta.
Okay. So on 28, okay? So on 28, start with this idea. So remember, this is how your book gives the equation for electric field in a capacitor. It has this dielectric constant. How, don't worry about it, it's 1.
Why is it called cow?
It's big.
It's the
Can we
Greek
get to the
letter.
point?
Oh.
It's C-A-U, not P.
Oh, okay. I was curious, I'm sorry.
Curiosity killed the cat.
Okay. Or the cow. So functionally, don't worry about the cow value. Your 1 over epsilon naught is a fixed value. Okay, that's not changing. So the short version is that it's a ratio of charge to the cross-sectional area. Okay. We're good with where I'm at so far? Okay.
What do you do?
So on 28, it says what it's trying to figure out is what's going to happen as a ratio to the final to the initial if Q is doubled. So if I double the value of Q,
Wait, never mind. I thought there were 2 plates. And like it was talking about the electric field. Oh, I got them.
it is 2 plates. But this charge has to be the charge on, you can't have one plate with more charge than the other. So Q is just the charge on the plate. Don't make this complicated.
Oh. I thought it was like you had one like, and then the other K, and then like a ratio between.
No, it's like, well, here's one set of conditions. That's it. So yeah, I mean, do not make this complicated. So if I double the charge, everything else is constant, what's gonna happen? Yeah. Let me see. Huh?
So it's 4 times and it's 4.
Come back.
Hey, L is half. And L is squared.
Your answer to 42 should start with a 1.
Oh, yeah.
Let's go.
Like double your or like all quadruple your age.
Your answer is 68. It should start with a 5.
Oh.
Yeah.
Is that in centimeters?
It's just saying it starts
I
with
think the way it's the way it's
Oh, never mind.
depending on whether you
What
want
is
meters or
that?
So wait,
Yeah.
No, I have. If it's in centimeters, it's about.
So if I were to be in meters, but it'll be times 10
Okay.
That's this first non-zero value is a 5.
Is that what wait, wouldn't A be
All right, are we good? Now let's talk about the sheet with the questions on that. Huh? Let's talk about it.
I was super lost in this and I forgot you said like
I did. I wrote it out step by step.
the questions at
Or am I
first.
thinking?
No, I literally gave you a step by step guide of how to answer this question. Okay? I literally laid it out. So, if you look at this problem, my bad. That's on me. So, I want to make sure everybody's cool on how you even start this. So, here's your X and Y coordinate system.
You got 1 for it.
You got a positive Q here, positive Q over here,
Oh, 20.
and a negative Q here, and everything.
Good
is
question.
a radius of.
Yeah,
No,
Right.
for the problem.
hey, I still need help on that.
You want me to help you?
Isn't it too late? So we just disagree on the answer. We just disagree on the answer.
To which answer?
28.
28
If his answer were to start with an F and mine were to start with a T, who would you make a?
Did you get 4?
What?
How did you get 4?
Because there's 2 cubes.
Shut up.
The F or the T?
No, the Q is the overall charge.
Ooh.
But like what?
Who's right again, bro?
Give me your pick.
Which page?
It's the overall charge. It isn't the charge on an individual plate.
Yeah, Wyatt. Yeah, I got it.
Okay?
Yeah.
Sign out to it.
Is that what you got?
That is what I have written down on my paper.
Okay.
What did we put on?
So on that extra set of questions, this will make sure everybody started the same way. It says determine the electric field created by Q directed towards the origin. So, what 2 things do you need to know to calculate an electric field?
You need to know the charge and the
Sec.
distance. The charge and the distance.
Not sec. We'll do KQ.
The charge and the distance.
I think we're gonna need Q.
KQ over R squared?
Hey, guys.
Okay? KQ over R squared.
Yeah.
Cool?
See.
Now, you're talking about this positive charge over here. If you're in the origin,
Yeah.
which direction is the electric field going to point based upon the positive Q?
Outward.
Wait.
Is it going to point toward the origin
Toward.
or away from the origin? Toward. Why?
This is
Because
positive.
it's in the positive net.
The positive test charge would feel repulsion. So the electric field at the origin
Yeah.
is literally going to be KQ over
R squared.
R squared.
way.
Now, is that going to be a positive or negative